I know.
Okay, let's bring it back together in 5, 4, 3, 2, 1. Awesome. Who wants to go first? Or I will just randomly call on someone.
I think we do the
Eric, Taylor, what do you know?
Look at the Lewis structure,
So you're gonna look at your Lewis structure.
and if it has 3 electrons on it.
Good, we're looking for those long free electrons. What do you know if you see those?
It's polar.
It's gonna be polar. Good, that's probably like the number one way we can know it, polar, non-polar. Okay. Let's see. So I'm gonna go ahead and show you guys a couple examples. We'll just shout it out. What do you know? Is it polar or is it non-polar? Okay, so we'll just build a few of these, kind of start here. Okay, here's your first shape. Polar or non-polar? Non-polar. What about now? Polar or non-polar? What is it? Non-polar. Good. What about now? Polar or non-polar? Still non-polar. They've all been non-polar. Okay, what about polar or non-polar? Polar. Good. We got those lone electrons. Excellent. Good. What about, let's do this. Oh no. I didn't want to do that. What about this one? Polar. What about this one? Also polar. Good. It's feeling okay? This isn't too crazy. We're just looking at 3D shapes here. Okay. Let's see. Actually, I wanted to give you guys a couple of real ones. I'm just curious, what do you think? Polar or non-polar? Polar, good. Okay. What about, some of these are really, really crazy. What do you say about this one? Non-polar. Good job. Awesome. So proud. You guys are killing it. Very well done. Okay. Go ahead and get those notes out and go to page 5.
It's been a while. Last time. Well, depends what sports rack or that you stepped into or the one that's
Page 5, guys.
the one that you stepped into.
Hopefully we can finish material today.
You ever have like a day try it. It's like so if you have like a date.
All right, guys. Page 5. Get those notes out.
I was actually. You want to hear about that?
Like instead of both being here, like you have to
Page 5.
like one
Yeah, but it needs to feel like much lighter.
All right. All right, guys. Okay, the goal again, like I said, is we want to try to finish material today. The concepts we're going to talk about today are, I would say they're kind of different than what you guys have seen before, but I think you'll be okay. I think we can do this. Before, we talk science, we got to talk English for a second. You're thinking, what the heck, Mrs. H? So there's a couple root words we need to be familiar with. These are those root words. The root inter and the root intra. Okay. I'm going to, that is pretty neat. I'm going to try to illustrate this using a game you may have played when you were in elementary school, maybe middle school, maybe you still play it. No, it's a different game. I'm going to draw a picture and you guys see if you can figure out the game we're playing.
Hangman. I thought that was like, they don't like bandits in elementary schools. They like band.
Red Rover.
Is it Red Rover?
Kill
Is
it.
that Rover?
What the heck is Red Rover?
They also have that.
I bet they did.
Oh, it's send someone right over.
Yeah, okay.
So many people don't know what Red Rover is, so can we have a little?
No, like
genuine.
Yeah, who wants
volunteer?
Who wants to break their arms? Lexi already has a broken foot, so she.
Demonstration, let's do it.
I've got a pretty good, I've got a good GIF I'm gonna show you guys. So hang tight, I've got a GIF. Okay. Okay, so just hold on. I would love to hear some glory stories in just a second. But okay, so just so we're clear on how Red Rover works, you're on the two teams, everyone's holding the hands, and we're trying to make a big old barrier, right? It's adorable. And then someone shouts out the magic words. They say, Red Rover, Red Rover.
Your voice Stockton right over.
Send Stockton right over. And then Stockton's like, I haven't drawn Stockton yet. Let me draw Stockton really quick.
Yeah.
Stockton's like, I'm Stockton.
That is so Stockton.
I'm your boy Stockton. I'm just smile.
No.
I'm your boy. Notice
I'm
how-
Stockton.
Notice how Stockton has a bigger
Oh,
brain than
okay.
all the other children.
Okay. So then Stockton is like, all right, well, I'm gonna go for it. And he runs his legs over there and he slams right into him and tries to break the bond right between their hands, right? This is Red Rover. This is the
That's
first
a game?
time. I've never heard of this game.
Dude,
Red,
this is the
hey,
best.
Red Rover is like the first time you break your arm, it's gonna be doing this.
Big bandit.
It's almost, it's kind of like
Oh,
football.
man.
Like you have a line, you just have to get through.
And you just get through. Okay. All right, I'm gonna show you guys a GIF really quick. This one is super important. Here's the GIF I'm gonna show you. Right. This is like the reason Red Rover gets banned.
See?
Bro,
You literally like
Yeah.
What are these people? It's like they're at this head level.
Yeah, see, this guy made a really bad choice. If you're gonna play Red Rover, you gotta jump in at like the torso. You can't jump in at the neck. That's like-
and then like you land on your face, break your neck, you'll die.
Yeah. Ah, freaking Red Rover. It's just such a bad time.
I'm pretty sure people die stupid ways, so.
Perhaps.
Yeah, people
Perhaps.
have many things, 360 times.
Okay. All right. So let's talk about how this has anything to do with what we're talking about. Okay. So in Red Rover, there are two major forces or bonds at play. The first one you have is the force of people holding their hands together. Okay. So holding hands, you don't have to write anything down. You're just watching. Okay. So this would be, I'm just going to go ahead and point to those little interactions, right? That's going to be like these. Okay. Where the hands touch, that's going to be one of the interactions. Okay. The other interaction and the other force you're seeing, let me change colors, is the force that's keeping your body together. So the force that keeps your arm from flying off of your body when someone jumps and tries to, break it. Oh, he probably is a terrible partner. You don't want him on your team. Yeah, bad times. Okay, so this is the force that holds your arm to your body. Now, Okay, so every time I ask this question, they're always like, it's stupid. I'm gonna be sarcastic. Okay, which of these forces would you hope will be stronger? Would you rather, so would you rather have your holding hands have that get broken, or would you rather have your whole arm get ripped off your body?
Holy hands.
I'll sacrifice an arm.
You would not. You would not sacrifice an arm. That's false. Fake news. No, you're not doing that. Okay. So you're really gonna hope that your arm's gonna stay on your body. You really want this to be stronger. And the holding hands of the people next to you, that might sometimes break. That might be just a little bit weaker. Yeah. Also more awkward. So, yeah. Or when your hands get all sweaty and you're just like, or someone ate some Cheetos and didn't wash it and you got Cheeto on you now. So bad, so bad. Okay. Okay. Let's bring it back for a second. I'm still trying to illustrate a point here. And so you guys are doing good. You are you're helping me out a little bit. Has anyone ever played intramurals? Intramurals. Yeah, when did you play them?
6th grade.
6th grade. So middle school or elementary school? One of those. What did you do for intramurals?
Like lacrosse, and I also think I did ultimate frisbee.
And did you play games with people at your same school, or did you get together with other schools?
Same school.
Same school. Okay, so 6th grade, it was at the same school, and you just got together and you played games together, right? Okay. Who else has done any form of intramural? PE is basically a big old intramural. This is free for all, right? The other thing that you may know about is intercollegiate sports. So there's a few colleges around that maybe you're familiar with, right? USU is super close to us. Maybe you're familiar with BYU. Maybe you're familiar with the University of Utah. Maybe you're familiar with a school that's actually good at sports. Weaver, other places. Okay, so in intercollegiate sports, let's say that USU is going to go and play football. Are they going to play themselves? Like, are they going to just play? No, they're going to play someone else at a different college, right? So they're going to go play someone else. Maybe they're going to play UNLV or LSU. Yeah, they're going to play some other different university. So intercollegiate sports is when there are different universities coming together to play sports, right? Intramurals, that's when you're in the same place. And they do this not just in 6th grade, but I played intramurals when I was in college. And when you sign up and then you just go play against other students that are at your same university, right? So it's the same school, same place, okay? The root inter means between. The root intra means within. Okay. Let's go back to our little example. So let's see. Okay, so let's say that you had a molecule. Let's just say we had the molecule water. Okay, here's water. Here's another water. Okay, let's look at this bond right here. Or it could be this bond or this bond or this one. And it doesn't matter. Any of these bonds are happening within the same molecule, right? So this water is one molecule. These bonds are within or inside that molecule. So this would be like an intermolecular force. Sometimes we'll be able to see that there can be interactions between different molecules, right? We have two water molecules up here. Sometimes you can see that there are interactions, and those interactions are called intermolecular forces. So we're just differentiating between inter and intra, okay? Up until this point, we've talked a lot about intramolecular forces. You guys have a little table. It's on the very top of page 5, and it looks like this, right? You got it? I'm trying to think. First one, is the first one intra or inter? Intra. Okay, so we have intramolecular forces. These are ones that you already know about. What's a force? A bond that holds molecules together. There's 3 of them. Who can tell me one of them? Which is a type of what? Covalent, right? That's yeah, polar. Okay, so covalent. What's the other one? What's another one, you guys? Ionic, good. And what's the other one? Metallic. So an intramolecular force is a bond that holds a molecule together. Okay, covalent, ionic, metallic. We've talked about those up till this point. Now, today what we're going to talk about are the intermolecular forces. And we're going to list them. There are 3, and you can fill this in as we go. But they are different. Okay, I want to go back to our example of Red Rover. Yes. Here's the thing. Everyone second hour has to play too, but I feel like maybe 4 people want to play, and everyone else is just going to be like, my arm is going to get broken. And then it's like, saddest thing ever.
I think there's actually more people.
How about this?
That were playing here than
Is anyone actually going to be here on Friday?
no.
What about if we finish the test on Thursday when you're done with the test?
Yes.
Maybe I'll let you guys.
4 corners.
4 corners. Do you guys remember when we played periodic table chase all the time?
Yes.
Oh, one more time.
No! Okay, let's go back. Okay.
We need to have like one more time and
Yeah, we do. Okay, that's the quote. That's the quote. Okay, back to Red Rover. So this is kind of like these 2 forces, the holding hands and the holding your arm to your body. One of these is an intermolecular force, and one of them is an intramolecular force. So we're talking about kind of analogy. So I want you to think for a second, so your table partner. Which of these would be intermolecular between different molecules? Which one would be intramolecular, holding the same molecule together? Tell your table partner.
How do you play? So you go, and what happens when you get there? You win. That's not what I meant. What happened? That's it, bro. You're dumping it over break yourself.
All right, holding hands in Red Rover. So holding the people together. Nathan, what do you say? Is that intermolecular or intramolecular?
Enter then.
Why, okay, why is it inter then? You got- Stockton's always.
I said
Lucy,
enter.
hold up. Okay, Lucy, what do you think? Good, remember, if you're holding hands with someone, right, that's a connection between different people, right? Okay, so that's an intermolecular force, and it's pretty weak, okay? Whereas like if you're trying to keep your arm on your body, you know, it's a much stronger force, all right? And that would be like an intramolecular force. We gotta make sure that we know the difference. Intra, okay. But this horse is dead. We're gonna calm. Okay, one more time. The worse you played it, they were all.
They're like lifting it at level, like. We got
So
that
you
one.
guys, wait, did you guys get it down to everyone?
No,
Did
no,
they
no.
send out like a memo, they're like to all people, do not play Red Rovers? Whoa, don't play that. Did I tell you guys that, my sister-in-law, they got knitting masks from the school?
They got
Like knitting.
Wow.
No, because they would just sit there and like be knitting the whole time. Like, if you do any working class, they just all these people want to- So they found knitting. Okay, guys, back to page 5. There are three intermolecular forces you need to know. This is the first one. The first one is called London dispersion forces. Don't know why it's called London. Just name for someone. London dispersion forces occur between all molecules. You take any two molecules, you put them next to each other, they're going to have this very weak attraction, this weak attractive force. This occurs between all molecules. Probably the best analogy I have for this is all of us are here in this room together. We're just kind of aware that there's people around us. You're going to walk out of this room and most of these people, you're like, sweet, I'm not going to see that person until tomorrow, and you're going to be unfazed. Okay. Pretty much that's like London dispersion forces. It's this awareness of people around you, but it's not like it's pretty weak. Okay. Let's look at a couple examples. So we're going to draw a picture. I'm going to have you draw the N2 molecule, which looks like this. Okay, this is N2, nitrogen gas. If you had a nitrogen gas molecule next to another nitrogen gas molecule, look like this. I'm going to draw the intermolecular force in a different color. So these molecules would have, represented by the dotted line, kind of just this weak attractive force. That's our London dispersion force. If you drew the Lewis structure for Cl2, which looks like this. Yeah, this is nonpolar. You could also be able to have a London dispersion force between this molecule and the nitrogen, right? This is also a London dispersion. Give you any two molecules, they're always going to have London dispersion, okay? Always. Okay, can I go to the next one? The next one is dipole-dipole. So dipole-dipole are forces only found between polar molecules, and both molecules have to be polar. Dipole-dipole. Again, only between polar molecules. So let's go ahead and draw this. Okay. So we're going to draw a couple HCl's. I want you to draw them with their Lewis structures, the little dots. You're just going to draw maybe two of them. We're just going to draw two. Okay, so draw them kind of like that. Once you've drawn them, tell your table partner which one's going to have a partial positive charge, which element's going to have a partial negative charge. Between hydrogen and chlorine, partial negative, partial positive. What do you say? Eli, what do you say? What's got a partial positive? Good. So your little partial positive's going next to hydrogen, and you can put it next to both hydrogens, which means the negative has to be on chlorine, so our partial negative's on chlorine. Okay. So in a dipole-dipole situation, right, these are two polar molecules, and what's going to happen is the negative partial charge on this chlorine is going to be attracted to the partial positive charge on the hydrogen on the other molecule. So I'm going to draw a little dotted line right here. This represents the dipole-dipole. It's a bit stronger than London dispersion because of the opposite charges, but still definitely not as strong as like this covalent bond that's holding the HCl together. Questions so far? Is all right. For the last thing, we need a bit more color to draw what we're wanting to do. What I'm going to have you guys do is snag 2 colored pencils, one of these blue papers, and then hang tight really quick. I haven't finished my instruction yet. This blue paper, I'm going to have you tape into your notes. You're going to use a piece of tape no bigger than about 1 inch. And you're just going to tape it like up here. Tape it so you can fold it up. Okay, like a little Marauders map, right? Okay, Harry Potter, great. So got it. Okay, awesome. So piece of paper, thank you. Piece of tape, 2 pencils, all right? Ready, set, go. Okay. You're gonna tape it. You're gonna do this. Doesn't matter. Upside, sideways. All good. All righty. Okay, the last type of intermolecular force is called hydrogen bonding. Okay, hydrogen bonding is very specific. It's between polar molecules, but it only happens when specific elements are involved, and that is hydrogen, nitrogen, oxygen, and fluorine. Okay. Things that do hydrogen bonding have very interesting properties. They have really high boiling points. It takes a lot of energy to cause them to evaporate. And they also have lots of surface tension. Does anyone know what surface tension is? There's like tension on the surface. Yeah, like water. So have you guys ever seen those little like water striders? Little dudes that just like run across the water like Jesus bugs? Yeah, you guys seen those? Okay. I don't have one. Like.
Maybe you should show the same video.
Okay, we'll find it. All right. All right. You guys have maybe seen something like this. You go to like the
Watch it. Watch a video on it.
magic.
Go to the videos. I want to see it. I really deeply want to see it.
I feel like the video is interesting about picture books. Okay. So what? Maybe on Thursday or Friday. Not right now. Not right now. Okay. So those are some interesting properties. Let's go over to, let's see. Okay, so you're gonna draw this not on your blue paper, you're gonna draw this just underneath where it has the example. Okay, I want you guys to draw 5 water molecules. Okay, you're just doing this in the space underneath. Actually, you know what? You just do, okay, just do 3 of them. Just do 3. Just do 3. You're going to draw 3 water molecules. You're going to do this in the space underneath where it says hydrogen bonding. You got some space there. Draw them like this. Get them in that orientation. You're just drawing these 3 water molecules. Okay, these are just 3 Lewis structures for water. Once you've drawn your water molecules, you're going to take one of your colored pencils, and I want you to assign the partial charges to all the oxygens and all the hydrogens. Which ones are partially positive? Which ones are partially negative? Okay, you guys got it? Okay, now with hydrogen bonding, your rules are that we again have to have hydrogen, nitrogen, oxygen, or fluorine, right? We'll write a list of the rules in just a second, but what we're gonna see is we're gonna see that the positive hydrogen on one molecule is going to be attracted to the negative oxygen on a different molecule. So you're going to draw 2 dotted lines. You're going to draw a dotted line right here. And you're going to draw a dotted line right here. Okay, and make sure you use a different color. These represent the hydrogen bonds. We call them bonds. They're not really bonds. They're interactions. Okay, these represent the hydrogen bonds. Got them over here as well. All right. This is really strong. It's stronger than dipole-dipole, and it's what causes water to have surface tension. So it keeps the water molecules kind of together, which is why those little bugs can go ahead and walk all over the water. It's really cool. Okay. All right. Crazy stuff. Okay, let's see.
Part B in the notes. It's like a very strong blank only occurring between.
It's a very strong dipole-dipole. So it's like a type of dipole-dipole, but it's very specific. Yep, good question. Good question. Okay. Off to the side, I want you guys to write down these couple of rules. Okay, so here's the rules about hydrogen bonding. You have to have hydrogen involved, obviously, and you have to have either the element nitrogen, oxygen, or fluorine involved. Okay, so one scenario that can work out, if you have here's one molecule, here's the second molecule. On the first molecule, you could have hydrogen bound to nitrogen, and then on the second molecule, they just need to do some sort of attraction between a nitrogen, an oxygen, or a fluorine. Okay, and those are going to be able to do a hydrogen bond. Your other option is you can have oxygen with hydrogen, and it can hydrogen bond with a different molecule where there's a nitrogen, oxygen, or fluorine. Finally, you could have a molecule that has fluorine bound to hydrogen, and that can do a hydrogen bond with nitrogen, oxygen, or fluorine on a different molecule, right? So this is molecule 1, molecule 2. Okay. So it's just very, very specific, the elements that are involved here. Okay. All right, we're going to use the blue paper now. Okay, I have 3 scenarios, 3 little things we're going to draw on our blue paper. So if you guys flip it over, maybe you might need more space, but just, we're going to draw some Lewis structures. I would say for your Lewis structures, you don't need to draw them any bigger than about the size of a quarter. So that should work out just fine. Okay, blue paper, the first thing I want you to do is I want you to draw 2 ammonia molecules. Draw those Lewis structures, and I want you to draw them stacked. Okay, draw them stacked on top of each other. Give a little bit of space. Okay. I'm going to give you guys about a minute. You should be able to draw these. You should almost have this. What was that? Don't use a colored pencil. Just if you have used a colored pencil, that's fine. I gave you 2 colored pencils so that you could have 3 colors, right? Colored pencil 1, colored pencil 2, and whatever you're usually writing with. Okay. So we're drawing our NH3 molecules. Okay, you're going to use one of your colors, and I want you to label whatever color you choose. I'm using red. In red, I'm going to label my partial positive and my partial negative charges. So I'm just going to go ahead and draw my little partials. Hydrogen's got, is it partial negative or partial positive on hydrogen? Positive, so I'm going to put a little partial positive next to those hydrogens. And you'll get your partial negative next to your nitrogen. Partial negative, partial negative. Okay. Okay, now we just need to show where the hydrogen bonding is going to happen. Turn to your table partner, don't draw it yet, but show them where is the hydrogen bonding going to occur between these molecules. Meg, what do you say? Okay, so here's an H between this end, this end. Good. So pretty much right here. Good. Let's draw a little line right here. This dotted line represents my hydrogen bond, right? Between different molecules. Okay, it's right there. Question? What's your question, Jamie?
Your ammonium thing, isn't it like 4 hydrogen?
This is ammonia, which is different than ammonia. Yeah. Ammonium has NH4 plus, but ammonia is just NH3. I know it's kind of weird. Okay. Next one. So for this one, I'm going to have you guys give this one a shot. You're going to draw 2 hydrogen fluoride molecules. Do this side by side. After you've drawn, show the partial positive, partial negative, and then I want you to predict where your hydrogen bonding is going to happen. So the first question we have is which one is partially negative, what's partially positive? Grace, can you tell me which element's going to be partially negative? Fluorine, good. So put your little partial negative next to the fluorines, partial positive next to the hydrogen. Okay. And we're going to draw our hydrogen bonding. Jack, where do you think we should put our hydrogen bond? FH. The other one, good, different molecules. So we're going to stick it right here. So that is our hydrogen bond. Okay. Okay, last one. You need to flip over your paper, you can. For this one, you're going to draw an NH3 and an H2O molecule. It'll probably be easier if you draw them stacked. Okay, give you about a minute on this. All right, who wants to use the fun Apple pencil and draw where those partial charges go? Okay, give it a shot. Those partial charges. There we go. So you're gonna draw right now.
Oh, yeah.
Good job. Cool. So you should have labeled it so that all the hydrogens had partial positive and all of the oxygen and nitrogen had partial negative. Okay. Someone else draw. Where is my hydrogen bond going to go? Who wants to? Someone else. The heck?
Come on, guys, raise your hand.
No one. Everyone's a bunch of dead doors. Yeah, perfect, good, that works. Yep, awesome. Okay, good, so we got our little hydrogen bond between the hydrogen of one molecule and the oxygen of a different molecule. Good. Okay, good. Now this oxygen right here, it could also do a hydrogen bond with something else. So if there was something else present, it could do a hydrogen bond. Awesome. Okay, good. All right, go to the very bottom of page 5. Okay, bottom of page 5, you guys. I'm gonna have you do this with your table partners, okay? For each of these, A, B, C, D, E, and F, there's going to be at least one type, there may be 2, there may be 3, okay? So here's the pro tip on this. The first thing you need to do is you need to decide, is the molecule polar or non-polar? And then remember, there's 3 types. We've got London dispersion forces. I'm actually gonna write that out. London dispersion. We've got dipole-dipole. And we have hydrogen bonding. So those are your 3 that you have to choose from. Go ahead and go through A, B, C, D, E, F. Figure out, is the molecule polar or non-polar? What kind of bond do you think is going to happen? We'll come back together in about 3 minutes. Okay, chat it over to table partners, see what you guys think. All right. Here we go. Okay. Let's look at these first ones. Again, we got to look and say, is it polar or non-polar? So we'll just go ahead and write that below. H2, polar or non-polar? Non-polar. What about, okay, non-polar. So what type of interaction happens between non-polar molecules? Is it London dispersion? Yes, it is. Is it dipole-dipole? No, because they're not polar. Is it hydrogen bonding? No, because hydrogen bonding is very specific. They have to be polar molecules that have those we know is nonpolar. HCl, polar, nonpolar. Even, it is polar, good. So we have one nonpolar molecule, we have one polar molecule. What type of interaction do you guys think this is gonna be? Dipole, they both have to be polar.
Oh, so it's gotta be.
This one's also London dispersion. Okay. Alrighty. Okay, this next one, we have water. Water, is it polar or non-polar?
It's, polar.
Polar. Sodium chloride. This one's actually, it's actually ionic. It's got the charges though, right? So if it's ionic, it's gonna kind of behave like polar. So is this one gonna do London dispersion?
No.
Yes, it will, because everything does London dispersion. So yes, it will do London dispersion, but it will also do something else. What's the other thing it will do? Good. It's going to do the dipole-dipole. There's multiple correct answers on these. Okay, let's go to the next three. Let's see. It's going to kick me out. Wow. Okay. The next one was, let's see, it's just taking a second for this thing to load, so I'm just gonna wait. The next one was for D, sorry. Yeah, we're becoming a victim of technology right now. CH3OH, right? CH3OH, what was the other one?
And H2O.
All right, H2O, okay. Let's look at water first, because that's easier. Polar or non-polar? Polar. Okay, CH3OH, what do you guys think before I draw the Lewis structure, polar or non-polar?
Polar.
This one is a polar molecule. Okay, if I draw my Lewis structure, it looks like this. Right? Okay. And then if I draw water, water looks like this. Okay, so we know this thing's polar. Will this do London dispersion, yes or no?
Yes.
Yes. Will it do dipole-dipole? Yes. Does it meet the requirements for hydrogen bonding?
Yes.
It does. Okay, it does because remember hydrogen bonding, we're dealing with hydrogen and then nitrogen, oxygen, or chlorine. And in this case, we've got hydrogen and oxygen that we'll be able to deal with. So they'll be able to do a hydrogen bond. Okay. All right. So that one is all three. Okay. The next one, MgCl2 with MgCl2. Before even looking at anything, we know what kind of bond are we, what type of interaction we're always going to have. London dispersion. We're always going to have London dispersion. Okay. You guys think these behave more like polar or non-polar molecules? They're more polar. These are actually ionic, so they technically have like the charges, the full-on charges. And so these are going to be able to do, what's the second type? Dipole-dipole. They'll do both London dispersion and dipole-dipole. Okay. The last one was NH3 and NH3. NH3, polar or non-polar? What do you guys say? Here's the Lewis structure. Good, this one's polar. So you draw a polar molecule next to another polar molecule. Ty, what's one of the interactions it'll have? It will do hydrogen bonding, yep. And because it does hydrogen bonding, it will also do dipole-dipole. And it will also do London dispersion. So if it does hydrogen bonding, it does all of them. Can you guys see that little visual that I have at the bottom of page 5, all the circles? You guys see that? So those circles, this is the last thing I'm going to say, and then I'll let you guys try a couple on your own. Those circles help you guys kind of get the idea that London dispersion is the most inclusive. Okay, it includes all molecules. Dipole-dipole is specific to only polar molecules, and hydrogen bonding is a specific type of dipole-dipole only between molecules that have hydrogen, nitrogen, oxygen, chlorine. Okay, so with that being said, the last thing I'm gonna have you guys do, and once you check off with me on these, you are good to take off. Go to the top of page 9, very, very top of page 9.